Hello students, this is Commander Gish with Lesson 10, Wave Characteristics. So the next few lessons in this course are going to be about ocean waves. This is a very important part of the course. We'll talk about how ocean waves behave, how we can model them mathematically, and then how they interact with structures that we might build in the coastal or the littoral environment. So like many of the topics in this course, waves is a very complicated subject. Engineering students take an entire semester course on wave mechanics, and we are going to boil that down to about 2 or 3 days for you. So we're not hitting all the details. We're going to try to give you an overview of how waves work and just enough information to be able to understand some of the concepts here. So let's jump right in. Here's the roadmap of what we're going to cover, some basic terminology, and then we will classify waves and talk about some of their basic characteristics. So first, starting with some terminology. So the nomenclature is very important here, and all of the important variables are listed on the right-hand side of this slide. So we start with wave height is a vertical distance measured from the wave trough, or the lowest part, to a wave crest. If we talk about half of the wave height, that's called amplitude, and that is measured from the midpoint, which is also known as the still water level, to either a wave crest or a wave trough. And the horizontal distance between subsequent crests is called the wave length. So we've got wave length is horizontal, wave height is vertical. The time between subsequent crests, if you're standing in a stationary point and watching waves go by, the time from one crest to the next crest is called the wave period, usually measured in seconds. And then if you combine wavelength and period, you can get wave celerity, or speed, which is, so it's the speed of an individual wave crest, and it's simply the wavelength divided by the period. Frequency is 1 over period, so that's in units of cycles per second, or hertz. And the wave number is 2 pi over the wave length. And omega is radian frequency, which is 2 pi over f, or excuse me, 2 pi over t, sorry. So the radian frequency, omega, is 2 pi over the period. A very important notation here, we use the subscript 0 to indicate deep water conditions. So H0 is deep water wave height, L0 is deep water wavelength, and so on. And we'll explain in a minute what deep water means. And also the subscript of B indicates breaking conditions. So one of the key things about waves is understanding when and how they break. And if we're talking about breaking conditions, we use the subscript lowercase b. And this video here, you need to watch this. This is essential viewing. It's about 15 minutes long, but it's well worth your time, because this video covers most of the topics that we're going to cover in the next few lectures. So I'm going to pause and let you watch that, and then we'll come back and continue. So when we talk about waves, we're primarily talking about wind-generated waves. I think it's in the next lesson we'll talk about other types of waves a little bit, but the vast majority of waves in the ocean are generated by wind, and we classify them as deep water, intermediate water, or shallow water, and we'll explain what that means here. So that classification is based on the ratio of depth to wavelength. So we call that a relative depth. It's not an absolute criteria. It's a relative depth to wavelength ratio. And the critical value is a D over L of 1/2. So if the water depth is greater than half the wavelength, we consider that to be deep water conditions. And essentially what that means is, if we look at this picture here, you can see the particle path of individual water molecules, and we'll talk about that in more detail in a few slides. But what you see, and you all know this from experience, is that the wave action decays the deeper you go under the surface. So as I dive under the water, I feel less wave action, which means the particles are moving less, and at a certain point, once the depth is about half the wavelength, that particle motion becomes imperceptible. You can't feel it anymore. So any depth greater than that we consider to be beyond the reach of the waves. In other words, the waves won't even feel the effects of the bottom at all. So we call that deep water. If we get shallower than that, so water that's shallower than half a wavelength, we call that intermediate or transitional water waves. So intermediate, transitional are synonymous, interchangeable terms. And what happens there is that the bottom does start to have an effect on the waves, and it changes the speed, it changes the trajectory of the molecules, and it changes the wave height. So it significantly starts to change the behavior of the waves. And then if we continue to get shallower, we get to a point where the depth is less than wavelength divided by 20, and at that point we call it a shallow water wave. Okay. So the other thing that you see happening here is in deep water, the waves are nicely rounded. We draw it as a nice sinusoidal curve. And as the water gets shallower, the waves start to become more peaked, and we get a shape that's steeper and more peaked and less sinusoidal. So that's another characteristic of the shallowing of waves. Okay, this slide talks about the particle path. So if you imagine a seagull or any object floating on the surface, that seagull, as waves roll by, doesn't move very far. In other words, he doesn't travel with the wave crest. He essentially stays in the same place and follows a circular orbit. And it's the same thing with a buoy, or if you're floating in salt water as waves are going by, the same thing happens. And these little animations here, you should watch these. They're about a minute long each, but they do a nice job of simulating this particle path as well. Okay, so here's some more about the orbital paths. So again, in deep water, the water depth is greater than half the wavelength, so the particles never feel the bottom, so therefore they follow this nice circular orbit. There's no effect from the bottom, and the circular trajectories get smaller the deeper you go. So the radius shrinks until eventually there's no perceptible motion at all. In intermediate water, what happens is you start out circular, but because the bottom effectively squashes that circle into an ellipse, so you end up with an elongated horizontal ellipse. And as you go deeper under the surface, the ellipse shrinks in both the horizontal and the vertical directions. So you end up with a path that looks like this. And in shallow water, it's very similar. So you start out with an elongated ellipse, but as you go further under the surface, the horizontal length of the ellipse stays the same, and it squashes in only the vertical direction, so that by the time you get to the bottom in shallow water, the individual water molecules are moving back and forth in a straight line. So they're basically just traveling back and forth like this as waves go over. And if you've ever been to the beach and you look down and see the sand in the very shallow water at the edge of where the waves break, you'll see these ridges, and those ridges of sand that run parallel to the beach or to the shoreline, those ridges of sand are caused by this effect of the water molecules oscillating back and forth and pushing the sand up, and the distance between those ridges will be the wavelength of the waves. Okay. We saw on a previous slide that waves get higher and more pointed as they move into shallower water. And what happens is that there's a critical ratio of the wave height to the wave length. And when that ratio exceeds 1 to 7, then the waves are considered to be so steep that there's a good chance that whitecaps will form. So what happens there is the waves become so pointed, and the wind tends to blow the top off the waves, and that's what creates the whitecaps or the whitewater that you see oftentimes in the ocean or in the sea or in in a river. You can also quantify that as the angle between the two sides of the waves, and if that exceeds or if that becomes less than 120 degrees, then that's considered to be so steep that whitecaps will occur. So 1 to 7 is that critical ratio. Okay, so this slide characterizes and summarizes a lot of what we've talked about. So as waves move from deep water into shallow water, in deep water, again, the depth is greater than 1/2 the wavelength, and the waves in deep water are the water's so deep that the waves never feel the bottom. There's no effect from the bottom at all. When you get into intermediate water, then the bottom starts to have an effect. It changes the orbital shape from a circle into an ellipse, and the wave crests become more pointed, more peaked. And as we approach that critical 1 to 7 ratio that we just talked about, the waves can break. And breaking occurs when the wave height to water depth ratio is about 3 to 4. And we'll talk more about breaking in a later lecture. So this bubble here in the top left of the slide is very important. So this fact that period remains unchanged is a critical thing that we have to understand about waves. So as water depth changes, as the wave moves from deep water into intermediate into shallow, the wavelength of the wave can change and the celerity can change, but the period never changes. The period remains unchanged for the entire life of the wave. Wave train. So wave in an actual ocean environment, we don't see just a single wave of a single frequency. What you see groups of waves that group together and form what are called wave trains. And you've probably seen this if you go to the beach. Waves tend to come in sets or groups, and then there's a slight lull, and then another group will come in. So this is a difficult thing to describe without seeing it. If we had our lab, you would see a demonstration of this, and you can very clearly see a wave group form, and then this concept of group velocity. So the individual wave speed that we've already talked about, celerity, is the speed at which an individual wave crest travels, but the group travels at a different speed called the group speed. And what we'll find is that the group speed is always less than or equal to the phase speed or the individual wave speed, which means that when you see this visually, what you'll see is you'll see some individual waves appear to catch up to the group from behind, and then you'll see other individual waves appear to run out of the group in front. So it's this constant, waves are running into the back and running out of the front of the group, and the group is continuing to move along. So this little animation here, you should watch this. It's a simulation, but it illustrates pretty well this concept of group versus phase velocity. So take a look at that. Now mathematically, we can write group velocity as it's a function of the celerity, and it's also a function of wave number and depth. So we see here this hyperbolic sine function. This is pronounced sinh, and it's probably been a while since you've seen hyperbolic trig functions. So you should be familiar with these from your calculus courses, and you will want to make sure you have a calculator that can solve hyperbolic trig functions. You're going to need that for this course. So this is the equation for group velocity, and what this reduces to in deep water, we find that the group velocity is exactly 1/2 of the celerity, and in shallow water the group velocity is exactly equal to the celerity. So the group velocity always is somewhere between 1/2 and 1 times the celerity. It's never greater than celerity, and it's never less than half the celerity. And then what this all means is that gravity waves or wind generated waves are dispersive, and what that means is that the waves of different wavelengths or different frequencies will travel at different speeds. So a good visual for this concept of dispersion is, imagine a group of midshipmen lined up for the PRT. Everyone starts at the same starting line at the same time, and when the whistle blows, you all start running. But what quickly happens within the first couple of yards or the first half a lap is that the midshipmen get dispersed based on their speed. So the faster runners tend to run ahead, and the slower runners are going to fall to the back of the crowd, and you're not bunched up anymore. So exactly the same thing happens with waves. Out in the open ocean, during a storm, for example, waves of several different frequencies will be generated at the same time. So they all start at the same location at the same time, and they start traveling. But the faster waves, the ones with the longer wavelengths, will travel faster and will quickly outdistance the shorter waves. So that's what we mean by dispersion. This is a visual plot of the group velocity function as a function of celerity. So again, you can see in deep water out here at the right hand side of the curve is d over L greater than 1/2, characterizes deep water, and you can see that the CG over C ratio is 1/2. Whereas at the other end of the curve, the left end, is where we have shallow water, and there CG over C is 1. And in between, in the intermediate zone, it's something between 1/2 and 1. Okay, so this table, this table summarizes some of these key equations. So again, here's our criteria for deep, intermediate, and shallow water waves in terms of d over L0, the deep water wavelength. So anything greater than 1/2 is deep, between 1/2 and 0.05 is intermediate, and less than 0.05 is shallow. This equation here, deep water wavelength L sub 0, is always equal to gt squared over 2 pi. It doesn't matter what regime we're actually in, you can always calculate the deep water wavelength as just gt squared over 2 pi. So in all of these problems, we'll see some examples in a few slides, but the first step, if you're given period, the first step is always calculate your deep water wavelength and then calculate your d over L naught ratio to figure out what type of wave you have, whether it's deep, intermediate, or shallow. Once you know that, then you can use the appropriate set of equations to figure out wavelength or celerity or group velocity, whatever you're asked to find. Also, I'll point out in the intermediate range here, you see these approximately equal to signs for wavelength and celerity, and that's because in order to actually solve for the exact values of L in the intermediate range, it's actually what we call a transcendental equation. You can't directly solve it algebraically. So the only way to solve that is through numerical iteration, but this approximation is very close to the actual answer. So for this course, this is a close enough approximation. Okay. The other interesting thing you can note here, I just got done explaining dispersion of waves and how waves of different frequencies travel at different speeds. But you notice in shallow water, that's not true, because in shallow water, the celerity is simply equal to the square root of g times d. So there's no frequency, there's no period or anything in that equation. It's strictly a function of depth. So that's an interesting phenomenon. In shallow water, waves are no longer dispersive. All waves travel at the same speed in shallow water. It's just a function of the water depth. Okay, these next 3 slides are examples, and you have separate videos to watch and walk you through these examples. So I'm going to skip these. And this slide is an animation here. So the question is, what's right with this picture and what's wrong with it, if anything? So I'll give you a second to think about that. So what you should have recognized is that the waves moving left to right starts out in deeper water and it gets shallower as it moves to the right. And when the waves are in deep water, they're nice rounded sinusoids, and as they get closer to shore, it appears to get shorter. So the wavelength is getting shorter and the waves are slowing down. And those are both accurate depictions of what actually happens. Wavelengths decrease and therefore celerity decreases, because we remember that the period is constant. The period always stays the same. And we know that celerity is equal to L over T. So therefore, if L decreases, the celerity also decreases. So the waves start to bunch up. And that means that the energy has to go somewhere, so it goes into the wave height. So the waves actually get higher, so that's also accurate. The one part of this that's not exactly accurate is that these waves, by the time they reach the right edge of the screen here, are extremely steep. This wave height to wave length ratio is way more than 1 to 7. It looks like it's probably about 1 to 1 or 1 to 2. So these waves are steeper than would actually occur in real life. In real life, these waves would break or collapse long before they got this steep, but otherwise it's pretty good animation. Okay, so here's another little example. Imagine you're on a ship and you know that your water depth is 200 feet. That's an easy thing to measure from a ship with a fathometer. And you feel the ship bob up and down every 8 seconds. So you're timing this with a stopwatch, and you notice that the wave period is every 8 seconds because the ship is following the particle motion of the water. Therefore, the frequency with which the ship bobs up and down is the same as the wave frequency. So in order to characterize whether we're deep, shallow, or intermediate, we can calculate the D over L naught ratio. So we would calculate L naught as GT squared over 2 pi. And that comes out to be, I believe, 328 feet, if I remember correctly. And I can tell without even resorting to a calculator, I know that 200 feet, the depth, divided by 328 feet is greater than 1/2, which puts me into the deep water category. So this is a deep water wave situation, so I would expect circular particle paths like this. I think the exact value that you get, D over L naught, is 0.61 for this case. And that's about it for this summary, or for this lesson. So we learned the terminology, the nomenclature for waves, and the characterizations of deep, shallow, and intermediate. So we'll talk more in lesson 11 about some of the phenomena that occur with waves when they interact with solid objects. Thanks.